Hello, friends. Rather unusually, today we are going to be looking at something new. So, Chapter 7 is the place where the stuff that we did in chapters 1 through 3, also known as descriptive statistics, wherein you find some data and then you try to describe it both visually and numerically. And then we took a little detour into the land of probability, which is what we were doing in, chapters 4 through 6. Then chapter 7 picks up and says, why don't we throw those two ideas together and see what we can make of this? So you'll notice that it contains two topics in its title that we discussed previously: sampling and then distributions. So just as a reminder, distributions we've been talking about for 3 weeks now, actually 4 weeks. Oops, I can count. And they are really just taking the idea of if I have a variable I'm looking to describe, I can describe it in terms of the values that it takes on and how often those values occur. And then we're somehow going to join that with sampling. And this actually is pretty easy to do. All right, let's start off with some learning outcomes. So the first thing we're going to talk about is what sampling error is. We did have this in our notes earlier, but you probably have forgotten it by now, so I'm going to remind you of that, and it's a very important concept in statistics. And then we're going to look at determining the mean and standard deviation of a sampling distribution of a sample mean. You don't know what that is yet, but trust me, it's coming. Then we'll talk about what the central limit theorem is. It's a result in statistics that basically gives us everything we're going to do for the rest of the class. It's very important. That's why it gets a fancy name. And then we're going to talk about applying the same ideas to a sample proportion. So just as a reminder, a proportion is a count out of a total. So if you were looking to poll your class and see how many had recess when they were growing up, and you would ask them to raise their hands if yes they did, and you counted how many people raised their hands and said yes out of the total number in your room, that would be a proportion. So say if like 12 people raised their hands out of 20, that would be your proportion. So we usually represent proportions as decimals in case you haven't caught on to that by now. What are we going to talk about? Sampling error. So just as a reminder, a parameter is going to be a numerical measurement we get from a population. The one thing you need to remember about a parameter is that it doesn't change. It's always the same single value. Now it might change over time, like next year is different from this year when it comes to talking about what my population is, but it's important to keep in mind that throughout that year, that value does not change. And remember, it's your entire population. And the most of our goals for what we're going to do for the next 4 weeks is how to estimate a parameter, because in reality, you're never going to know what a parameter actually is. So, what do you do instead? Well, you get a simple random sample. And if your sample looks good or represents your population well, it should look like your population. And then you can use it to estimate what your population looks like. So we're going to focus on doing simple random sampling for today. There are other sampling methods. We talked about those back in chapter 1 if you want to go take a little review of that video or of your notes from that time. Because we're going to be using them a lot. So just a reminder, a simple random sample is we use a random number generator usually to generate it. One of my favorite places to get randomly generated things from is random.org. We're going to use that a little bit this week, and if you haven't checked it out, you totally should. It's a good source. All right, let's talk about sampling error. So sampling error is simply the difference between a statistic and the measure it's attempting to estimate. So the population parameter. So for when we're looking at means, that's when we compare the sample mean to the population mean. And for sampling proportions, that's when we compare the sample proportion to the population proportion. So just to give you some examples of each of these, this would be like, oh, I'm going to see what proportion of my sales came from new customers. I go out and I gather a sample of 30 customers, and I notice that, 14 of them are new. That would be a sample proportion. The actual value of all of your customers that were new would be the population proportion. And so this is a type of error because it's how far off you are. Remember, in statistics, errors don't mean you're wrong. It's just a measure of how far off you were. Okay. So it's important to note that the size of the sample error depends on which sample is being selected. So earlier I made note that, if you have a good sample, it's representative of your population, it looks like your population, then your sampling error should be smaller. But keep in mind, you can draw many, many different samples. It's just like if I sent you home and told you, hey, go ask 10 people you know, how many of you have an iPhone, and you counted how many of those people who did and came back. Some of you are going to say, oh, 100%, everybody I know has one. Some of you are going to come back like, oh, 50%. Half of the people I know like Android and half like iPhones. There's a distinct difference between each of your samples. Now, when you start to draw larger samples, you can actually reduce that. So you're more likely to get something that looks like the population because of size. That and, people who know each other are usually pretty similar in their behavior. Anyway. So for a quick little example, suppose we have a population where we know the mean age of our employees at a major automaker happens to be 45 years, and instead of using that population parameter, we're going to gather a random sample of 30 employees, and we'll note that the actual age is 38 years. So we calculate the sample error to be negative 6.5 years. So that means that the sample mean provided an average is that, 6.5 years less than the population mean. Usually we interpret negatives here as just saying less than rather than writing the word minus in our writing. This is just something I'm bringing up because it's one of those popular vernacular differences in language and how we write about things in sentences versus to communicate with each other instead of how we write them in mathematics, which is kind of important if you're going to be communicating some stuff to major stockholders. So if you're looking at this and asking, well, why would I bother with a random sample when I know the population parameter? Well, in most populations, you will not know the parameter. So it's important to note that when you think about sampling error and trying to estimate it, you're not always going to know what the population looks like. Okay, so suppose we look at a company and its office buildings, and we've got a total of 12 buildings, so we have the whole population, and you look at the square footage of each building, and then you do the average of those square footage. So I'm looking at these 12 complexes here, and then just as a reminder, how you do an average is you add them all up and divide by how many there are. In this case that would be 12, and you come up with the following mean. Notice this is a mu, a population mean, because it's all of the buildings that they have. If I'd only gathered a random sample, this would not be a mu, it would be an X bar because it's a sample mean. Okay, so suppose a potential customer plans to select a sample of 5 of the complexes from the 12. We notice that using our ideas from the binomial earlier, the chances of selecting 5 out of 12, there's 792 ways to do this. Now, I don't advocate you go out and do all 792, but if you have a computer handy, you can make it do it for you. And that could yield all the possible samples of that size. Now, once you have all the possible samples, you could look at all of them and see who is closest to the actual population mean, which we found back in the previous slide. All right, so if you pick the 5 smallest, so keep in mind the smallest, this would be not good. It would be the worst possible and the farthest from the average size that you could possibly get. Then you would obtain the following average. Notice it's the X bar because it's a sample mean. I've added these together and then divided by the number that there are, in which case there are 5. And then if you compare that to the population mean we found back in slide 7, you'll notice that the difference of them is about 50,000 square feet. So you have an idea of how big your sampling error could be by looking at the smallest in this case. Similarly, you could grab all the largest 5 in your sample and use that as an estimate for how large your sampling error could be. Hey, I knew this was coming, but I talked about it anyway. So here is the 5 largest. And clearly I'm doing the exact same stuff and looking at the difference between the mean from the entire data, the population mean, versus the sample mean for the largest 5. And notice that one is actually bigger. So in this case, the largest your sample error could possibly be is this 51,928 square feet. Okay. So if we look at the range of our sampling error, here is the possible range of values that it could be. If we similarly repeated the same process using only a sample of size 3, notice how much bigger the error is. So earlier I made a comment that, hey, if I want to fix the problem of my sample isn't close when I'm looking at the iPhones to the actual population values, one thing I could do is sample more people. Hey, I'm hoping what you see from this is even just increasing our values by 2, notice our upper and lower bound change significantly in tens of thousands of square feet. So what you notice in just using 3, it's a much larger range of possible square footage values of sample error from the size 5. So one thing we're noticing is that size seems to matter when it comes to our possible error if we consider doing random sampling. So Here's that in 2 bullet points. I forgot this slide was next. I feel like an idiot. Good times. Anyway, so what we notice is that, hey, it looks like sampling error is smaller for larger samples. So that means that if I want to make sure that I don't have an extremely large sampling error, I want to use a larger sample size. Let's combine these ideas into looking at many samples from the same population. So if you want to build what's called a sampling distribution, we're going to look at the distribution of all possible values of a statistic for a given sample size. So be thinking back to that 792 possible samples. This would be doing all of them and then counting how many had a specific mean to build a distribution. This is a complicated process that we will rely on technology to mostly do, but it's important for you to understand how this process comes about. So for instance, if we had 62 students who took a midterm exam and we constitute this as being our population, so this is everybody. Ooh, this kid, wow. Oh wait, I've got a couple of hundreds in here. Why is my font different all over the place in this one? Ugh, I need to fix this slide. Anyway, so we want to use simulation to estimate and derive for what our sampling mean and our sampling distribution might be. So keep in mind we're going to treat this as our population because this is all of our students. So what I can then do is then sort them. This will make it a little bit easier to sample from them and to derive what this might look like. You hopefully have noticed how I've arranged these in increasing order. All right, let's compute some parameters. So what I'm doing here is just adding up all of those sampling test scores and dividing by the number that there are, 62, and that comes up with an average of about 71 and 71.43. Remember, your mean does not have to be a value in your distribution. I know a lot of people be like, well, shouldn't I just round this to a 72 since nobody got a 71.43? That is not true. You do not have to do that. And then you notice our standard deviation is about 16.8. That's actually kind of a big standard deviation for a test. That makes me a little uncomfortable. If this was a real test, because it's not, I totally just made up these numbers, I would highly question how that test's results went through. Yeah. Just saying. Anyway, so take a look at this. This is the distribution of scores. So keep in mind, this is the population. So if we look at the number of people that were under 60, this is just a histogram of that. So it's a frequency distribution. I count how many people scored under a 60 in my original data. So going back here, that's everybody below here. Add those all up. You'll notice that there's 14 of those. Similar, if we go to 60 to 69, there's 10, 17, and so on and so forth. There's our mean. Remember, we think of the mean as a balancing point. If I imagine this like a teeter-totter, and these were little towers of blocks I put on top of them, this appears to be where my teeter-totter would balance. Just so you know. This isn't also a great range since I'm only producing 5 bins here. It would be probably better for me to increase my bin size and produce a better histogram, but we're going to live with this for now. Okay, so now what we're going to do is start sampling from this distribution. Now that we have some idea what the population looks like, we're going to gather samples. All right, so here's one sample. So in particular, just grab one sample of size 5, add together all of them, divide by 5, that gives you your mean. Go through the steps to do the sampling error here. So I'm just taking the mean, the sample mean and subtracting the true mean of the population and coming up with 1.3. All right. So in particular, since this is a positive sampling error, that just tells us that's, not bad. It's pretty close. It's fairly small compared to the size of the means themselves. Now, if this was something like 10, I'd be like, oof, that's really far off because that's in the same units. Sorry, that's not what I want to say. It's the same factor size as the mean itself. So keep in mind, when I say factor size, I mean where is the largest unit occurring. So this is the ones place, this is the tens place. So having something about the same factor size like 10 is not good. So this one, since it's in the ones place is the largest unit that occurs, it's a factor smaller, which isn't too bad. That's a good sign. If I then gather a second sample, this sample is not as good. In particular, its sampling error is a factor of 10 size big. So I would look at this and say, this is a bad sample. This is probably not representative of my population. But remember, when you're gathering samples at random, you can get bad ones that are this far from the population. So, wow. I got too excited writing this. It appears that I have found a sample that's pretty bad. Again, looking at that factor idea, this is the same factor size as our mean itself. Yikes, that means my error is close to being the same size as my population. That's not something I want to see. All right, 3 more samples on here. Some of these are better than others. So one thing that you hopefully are getting from these examples is when you gather random samples from your original population, your error can range quite a lot. I mean, sample 4 is the best because it has the smallest error. Now you may look at it and think it's negative, that's bad. Remember, I'm just looking at factor size. How large is it? So this is the smallest one. Anyway, so let's take 200 random sample values and calculate the sample mean. So these are random numbers generated using Minitab, and then it's a population of size 200. And then what we're going to do is we're going to randomly sample 5 elements from it. And so I just like pick the first 5. You know, if you take all those elements in themselves individually for all those different samples and then subtract them. Oh my God, I am doing this wrong. All right. So I'm hoping you notice these first 5 match my 5 here. Yeah. Da 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 da. Okay, that I should stop doing because it's going to make you dizzy. So what these are is I did 200 random samples and did their means. So these are all of my X bars. So these are all means. Okay, they're not individual scores. They are means. I went and grabbed 5 people's test scores from the midterms 200 times and did their average, and this was the result. So if we take those and then we take them and subtract the mean from them, we get their sample errors. See how these vary quite a bit. Got some negatives, some positives, some big stuff, some little stuff. I can take those and then build a distribution. So what this is I took all those sample means back in slide 23, and then I stacked them together into a histogram. Now what do you notice about this histogram? Hopefully you notice it looks fairly symmetric, it looks like it's got one mode, and it almost has that nice shape we love from chapter 6. It looks kind of belly, doesn't it? Bell. Gee, I wonder if this is always going to happen. Hint, hint, wink, wink. This is what we call the sampling distribution, because it's the distribution of a bunch of samples. All right, so keep in mind, looking back, our original population has mean 71.43 and standard deviation 16.8. If I look at this distribution, so all those samples, those 200 samples I gathered, it has mean 71.25 and standard deviation 7.91. So its standard deviation is significantly smaller, but look at the population parameter. The mean of this distribution is very close to the original population mean. This is something that we're going to see is always true. Okay, so sampling error can be small, could be large, and it really depends on the sample you're looking at. If I do lots and lots and lots of samples, it appears that the mean of all those samples when stacked together into a distribution looks like the population mean. However, when you start doing samples or groups and averaging them, you get a lot less variation. Remember, when we say variation, we are thinking standard deviation. So since my standard deviation was smaller for my sample means, I get a lot less. So if you're having a hard time thinking about this, usually a good thought process behind recognizing why should the standard deviation be smaller, I'm going to ask you a question that hopefully helps. So which is more likely? One student in a class of 28 is over 6 feet tall, or the average of a group of 10 students from a class is over 6 feet tall? The average is much less likely to be that high because you're averaging across a group, and when you combine units like that, you lose the extrema. That's one of the reasons why it varies so much less, because you're more likely to grab values that are typical, if you want to think about it that way. Hopefully that helps. Anyway, so let's try this again, but I'm going to do it with size 10. So keeping in mind this is what I'm up to, gathering lots of samples of size 10. Again, I'm keeping track of sampling error, so I know how big or small I might be. We're going to do it 200 times again. I used a program called R to do this because it does it much faster than Minitab will. That's one of the reasons why we're not doing that with Minitab this week. Just, keeping that in mind. Anyway, so here's the sampling errors for those. Same thing. Stack them all up. Hey, take a look at that guy. Does it look more normal than the last one? Does it look more symmetric? The symmetry on this one's much nicer. And then if you do the mean, you'll notice that it's very close to the original mean. And then the standard deviation, it's much smaller, right? Because we're less likely to get these extreme things. In order to get a mean of 100, I had to grab 10 people in the original population that had a score of 100. Well, there weren't even 10 that had that. Yeah, there were only like 5. So, hopefully that helps. Anyway, so larger sample sizes, less variability. These things I've not highlighted because we've already talked about them. So we're clearly seeing that the bigger it gets, it seems to be the less spread, aka the smaller the variance of the sample means. So when you read this, I read it as the mean of the sample means because it's the mean of the samples. And then this is the variance of the sample mean because remember x bar means sample mean. So it's talking about the mean of this distribution and the standard deviation of this distribution. Alrighty. So, hey, here's the original, here's a size 5, here's a size 10. What are you noticing happening here? My centers of my two sample means, or my two sampling distribution means, are close to the original population, with the larger one being closer. And the larger I get in my sample size, going from 5 to 10, the more normal this appears to look, the more symmetric and the more unimodal it appears. And my spread seems to be getting smaller. If I take a population and I want to find its mean, what I can do is do many means of a certain sample size and then look at the mean of that distribution. It will be equal to the population mean. So what does this say? This says that when I look at original population mean, if I gather a bunch of samples and do their mean, it'll be close. So if you look at the size 5 and 10 from the test score example, that's exactly what this is saying. Theorem 2. It appears that when I do this, I get a standard deviation that gets smaller based on sample size. In particular, here's the formula for that. If you want to go back and check, you can see that this is absolutely true. Here's how you can do that down below. If I take 16.8 and divide it by the square root of 5, I get something that is very close to the actual one that we had in the sample. And if I repeat the same thing for 10, it is very close as well. So in general, this is what we are going to use as the spread of the sampling distribution. Ta-da! So what does this mean? If I start with a population that's already normal and I sample from it, when I take the samples of different sizes, it'll stay normal looking no matter what I do. And this isn't all that surprising. My samples look like my population. This is true if you do good samples, but when you're doing the sampling distribution, remember, you can get samples of any size. So that's saying no matter what happens, even if you get bad samples, as long as I do enough of them, it'll look like the population since it was already normal, which is a really awesome result. Here's an even more awesome one. This is the central limit theorem. So as it turns out, it actually doesn't matter what the original looks like. No matter what population I begin with, it will always look normal, as long as I sample large enough. And that's where things get a little wonky with this. So what do I mean by that? So regardless of the original shape of the distribution, it looks normal. So I'm going to roll back real quick. Did this original population look normal? Nope. But its sampling distributions did. So here's some funky examples. Here's some funky examples for you. So here's an original population that looks very strange and very non-normal. The first sampling distribution is size 2 for that. Looks like a fun triangle. That's, rather unusual. But then once you hit 5, it already looks normal. So you actually don't have to go any bigger than that, which is kind of fun. And if you start with the triangle as your original population, you can get there normal by just going to 5 like we saw down here. Let's go to the weirder one. So if you have what's called a heavy side distribution, where it's very, very skewed, where one side is much heavier than the other, it takes a little bit longer for it to look normal. So this is size 4. Notice it's got that weird heavy side to it as well. And then when you start looking at about 25, that's when it's going to start to look pretty normal. So I want to show you a cute little animation that you can play with to prove this to yourself. So, ta-da! This is only a shot of this because I can't fit it on my full screen with it recording, unfortunately. So I'm going to hit begin. Come on. There she goes. So if you start with something normal, what I'm going to make this do is I'm going to have it keep track of the mean for 2 different sizes. So for this first distribution, I'm going to be doing it for size 5. And for the second one, I want to keep track of the mean and have it do it for size, I don't know, 10 for fun. Now, I'm going to show you what this does. So if you hit animate, it's going to show you drawing that sample. So here's my sample of 5, do its mean, there it goes. And here's my sample of 10, do the mean, plops it on there. So and it keeps track of the means for you. Now, because I'm lazy and I want to make this do a lot of samples so I can get the sampling distribution, let's have it do 10,000. Bloop. Looking pretty normal, right? Ooh. Now take a look at the mean of this sampling distribution. It's 16.01. Hopefully this isn't too small for you to read. Actually, let me try zooming this in a little. There we go. That's better. Sorry about that. I should have did that to begin with. Very close to the original of 16, and the same thing with the following sampling distribution. Notice the spreads, much, much, much smaller, aren't they? Oh yeah, so I'm going to clear the lower 3, and I'm going to start with something that's not normal. I'm going to start with something skewed. Alright, so I'm going to keep doing the same thing, 5 and 10. Let's just animate one of them real quick so you can see what happens. So I keep in mind with skewed, since I have a heavier left side, I'm more likely to draw things from the left side than from the right, so this stuff is more unusual, and as I start to average across many, it's going to be much harder to get things in the unusual tails. Aha, so I've gotten unlucky here. Normally, when you have something that's a little bit normal, even if it's very skewed, if you've got one peak, it'll come out kind of normal anyway, which is something we don't really talk about, but it's a corollary to the central limit theorem. Don't worry about knowing that so much. Let's mess this up. So I like this animation graph because I can actually make this distribution as ugly as I want to. So let's make it like lumpy and kind of terrible, because I want to make something that's really unbalanced. So I'm just taking this and changing it up. I want something non-symmetric, non-normal, and like just really funky looking. So you can see what'll happen with something really skewed. So I'm going to clear the lower 3, and let's do the 10,000 real quick. Damn it, it came out normal. Clear. Oh look, it came out normal. Are you shocked? You shouldn't be. Like, it's something that's gonna always happen. Because it's the central limit theorem. I can mess this up all I want. Let's make it look like that. There we go. Clear lower 3, do it again. Normal! Yay! I don't know if this helps you believe me or not, but I'm making this distribution by just drawing on this and changing the heights. And I always get normal, so, you know, it's a good time. I don't know what else to say about this. I spent too much time on that. Okay. So, as long as I pick a big enough sample, then I should be able to get something that looks normal. The most important thing for this is that you should keep your sample size to something greater than or equal to 30. What's funny about this is, like, back when I was a student, they thought it was 20, and then they did some interesting estimating and discovered, nope, 20 is not enough. Sometimes it doesn't work. So 30 is the new number for this. So you've finally reached the cutting edge of statistics to where you've reached some stuff that we're still investigating and trying to figure out how big is big enough. Interesting, maybe. I don't know. Let's find out. So since our spread changed, so does how we do standardization. So how we do z-score has changed. So if I have a sampling distribution z-score, I'm going to end up, you know, using the sampling distribution standard deviation. So I'm going to end up dividing by the square root of n. So it changes things. So in particular, for example, if I'm looking at some French fries, so if you're looking for like operation consistency with your construction of products, sorry, not construction of products, production of products, you're interested in what we call quality control. So a food processing company has French fries for fast food outlets, and they want the distribution of French fry length to be normal with a mean of 4 inches and a standard deviation of 1 inch. They want it to remain relatively the same size, is what it's saying. Now, what's the probability of selecting a simple random sample of 100 fries with a sample mean exceeding 1.4 inches? So notice what they're asking for here is a sample mean, not a value on X, but an average being a certain value. That's how you know you're on a sampling distribution. It's asking about a sample, not a single fry, a group of them. Hundreds of them, actually. Well, 100 of them. So I know the sample size I'm using here is 100. My mean is going to be 4 because that's the mean of the original distribution. Since it's relatively normal looking, they'll match. And then my original standard deviation of the population is 1 inch. So If I graph this, notice I've marked the mean of 4, and here's the sample mean of 4.1. I want to figure out what's the probability to be bigger than 4.1. This goes back to things we were calculating in Chapter 6. Can I do a normal probability? Yeah, I can, but I gotta be careful. In particular, I have to be careful because the spread I need to use is the sampling distribution spread, not just sigma itself. So this should be 1 divided by the square root of 100. So when you calculate that, you actually get a z-score of 1, which means when you look this up on the table, you'll get a 15.87. Edit that part out too. Okay, what's the probability that we're looking at a sample of 100 fries and we end up with less than 3.8 inches as our average? So again, X bar, I'm doing a sample of a group, not an individual. So if you want to think about this another way, hey, I want to know what's the probability that my team score is going to be below this rather than just one member of my team. I've got to do a group. I'm doing a group. Yeah? Sampling. Anyway, so we're just going to go through, take our sample mean of 3.85, subtract the mean of the population, which is 4, divide by our standard deviation sampling distribution, our standard deviation of the sampling distribution, which is 1 divided by the square root of 100. You're always dividing by sample size square rooted, which feels kind of natural when it comes to standard deviation, because standard deviation is always involved roots of some kind. And when you do that, you get 1.5. Looking on our normal table being less than 1.5, remember, that's strange on the table because the table does between 0 and, oh, that bar is in the wrong spot. I'm not going to fix it. Is between 0 and that, so you'll have to do 1 minus it, or a half minus it, sorry. One thing to be careful about this is, yeah, you can just do mini tab with this, but you've got to use this spread to do so, not the original population. Okay, so if I want to look at sorry, my voice is losing it. If I want to look at a qualitative variable, one where you can count stuff instead of a quantitative variable, then I have to be using a proportion. So things are going to change a little bit when it comes to using proportions for a sampling distribution, but not a ton. So it is a little bit different just to prepare yourself. In particular, so for a population proportion, we just use p, and for a sample proportion, we use p hat. So it's like a bar, like the x bar. I was always meant to do a statistics because I'm an R bar. That was a bad joke. Similarly, my sampling error is always my sample statistic minus my parameter. So it's just the difference between the two. So of course, just like before, you would determine the population proportion, calculate your sample proportion, and then calculate the difference to get your sampling error. Remember, sampling error is just a measure of how far off you were by using a sample instead of a population. Alrighty. So the best estimate for our population is always going to be our sample, but just like we saw with means, you need to be big enough to make sure it's a good estimate. So with means, we needed to have at least 30. With population proportions, we're going to have it so that our sample size is sufficiently large. So if we do n times p and it's greater than or equal to 5, then it's reasonable to assume that it's going to look normal. So this is coming from the binomial itself. I have to have at least this many successes to be able to be successful in getting a normal distribution. All right, so what's the mean and standard deviation going to look like? Well, the mean is just going to be the proportion, and the standard error is going to be p times q over n. So if you look at this, this should look fairly familiar. This looks like the distribution for the binomial because it is just that. It is just that. So if you remember, the mean for the binomial was n times p. Well, I'm doing the average of a group. So how do you do the average of a group? You divide by the size n. If you take np and divide by n, you just get p. The same thing is happening over here. I'm just dividing by n because I'm averaging across the group. And as always, the standard error is using a square root. So you'll notice we call this the standard error because we're going to be using p's in here, and that's usually coming from the population. Sorry, it's usually coming from the sample, not the population, so it gets a slightly different name. Don't let standard error fool you. It is still a standard deviation. It just has a slightly different name. If you mess this up, I will not care. So just remember, standard error, standard deviation, same deal, there. Same deal. I don't know why I was trying to say something there. It was weird. I'm tired of talking. Anyway, so regardless of what I'm looking at for any sampling distribution or proportion, as long as my size is sufficient, so as long as I have at least 10 successes, or sorry, at least 5 successes and 5 failures, when I look at the mean of that distribution, it'll have p as its proportion, and its standard deviation will be p times q over n. So q is just 1 minus p, and I keep saying that. Anyway. Woohoo! So according to past records, we're doing an example now. When I look at a retail chain, the proportion of customers who pay for their merchandise with a debit card is about 60%. A particular store chain takes a sample of 100 customers and they notice that only 48 of those customers use their debit card. What is the probability that that sample proportion or less is what's happening in the two population? So what you might be asking yourself is my store different than the rest of the national chain? Let's find out. How likely is it that I got this sample or something smaller? So probability that my sample proportion is less than or equal to 0.48. It's 0.48 because 48 out of 100 is 0.48. And we're using 0.6 as our original population. So here we go. This is a graph of the, notice the mean is 0.6. And there's my sample proportion. And so I want this area over here, the stuff less than it. So the first thing I'm going to do is set up my distribution by finding the mean, which is just the proportion, 0.6. of the population, and then I'm finding my sample standard deviation, my standard error, by doing p times q over n, so 0.6 times 1 minus 0.6, so this is 0.4, divided by 100, and then take the square root. Be careful with your calculating there. And I've rounded this. These are always very small, so be careful not to round these too much. It can happen to you, it can happen to me, it could happen to anybody, you got to be careful. Real quickly, if you check to see what n times p is, so that's 0.6 times 100, and you'll get 60. That's clearly bigger than 5. And then, obviously, if 60 out of your 100 is bigger than 5, then the stuff that's not in there is 40, because, 0.4 times 100 is definitely bigger than 5 as well. Usually when I'm doing this, I'll only check the smaller of the two proportions, because, well, if the small one works, the big one will. Yeah, I'm just lazy about it. Anyway. So when we want to check to see if we want to find our probability. What am I doing? Anyway, so I want to find my z-score, so I take my sample proportion, subtract the population proportion, divide by the standard deviation. So this is just a z-score. Value minus mean, divide by spread. Value minus mean, divide by my weird spread. Remember, this is just the spread for the sampling distribution. And I get 2.4. That's a really large z-score. It's very far from 0. I think this is going to be a very small probability. Looking at our table, you have to be careful because it's going to be doing a left. Your table only does values between 0 and right, so you'll have to do 0.5 minus it to get this very tiny 0.001. So we were right by looking at z-score. This z-score, it's a very unusual value. Keep in mind, once again, this is a probability that you can do using Minitab, and we will be doing that this week. Alrighty, let's take a look at another example. So a taxpayer has been recently increased with, Let's look at another example. A big problem for taxpayers has been the recent increase of fraudulent tax returns. Dun dun dun. So the IRS is, in the name of all taxpayers, going to take a look at the proportion of those affected back in 2016. So this is, edging on the end of old data. So assuming the true proportion of taxpayers who get hacked, aka their IRS return gets discovered on the internets, is about 15%. What's the probability that more than 40 people in a random sample of 200 will have this experience? So it's asking, is this count unusual? So the first thing you actually have to do to this is turn that count into a proportion, because all of this is in terms of proportions. So we're going to do 40 divided by 200, and that's right here. So what we're really trying to judge, how far is 20% from 15%? And you might look at this and be like, oh, it's bigger, but be careful. Just because it's bigger doesn't mean it's really far away. The only way for you to really judge distance on a distribution is to look at the spread. Only way we do spread is standard deviations, so we really need the standard deviation to tell, is this far away or not? Let's get calculating. Okay, so we're going to set up our distribution by finding our spread. So you notice I've marked the mean, and then I found the standard deviation by doing p times q, so 1 minus, that's a typo, that should be 15. I'm sorry. Oh, it's going to be hard for me to fix this. So this should be 1 minus 0.15, just so we're clear, divided by 200, and then take a square root, because 1 minus 0.15 is 0.85. That's why I did this. Sorry about that. This is the correct value. Actually, let me double check that real quick. I'll pause for a second. Okay, coming back, yes, it is 0.085. So yeah. Anyway, so there's our spread. So you'll notice that I took the center value and then subtracted down to mark my spreads on the distribution. I've marked my sample my sample proportion on here, and I want to find this area. Now, with this example, since I have a sample size of 200, I'm pretty sure this is going to have both my number of successes and failures above 5, but it's worthwhile to check. So we're going to take 200 times 0.15, and for that you get 30, which is greater than or equal to 5. And I'm going to take 0.85 times 200 and get 170, which is clearly greater than or equal to 5. So I know this is going to look normal. I know it's spread. I know where this is located at. Let's do some calculating. I'm not gonna lie, I got lazy with this one and pulled out Minitab and then backtracked my way through the table. So now that I've got my spread, I can do my z-score. So I'll take my sample p of 20, subtract my proportion from the population, and that's 0.15, and then divide by the square root of the sampling standard deviation, which we found that earlier. We could have just used that value. Anyway, you get 1.98, which is very close to 2, so this might be big, might be small. Actually, this is going to be small, because using the 68, 95, 99.7 rule, that's going to be small. It's pretty far away. Anyway, so when you calculate that, you get 0.0239. I am reading numbers to you. God, that was horrible. Anyway, so what should you take away from this? If I sample large enough and I sample enough samples, I will get something normal. So a while ago, I told you, why do we want to do the normal distribution? Because it's the one we normally get. How do we normally get that one? By sampling large. Once you have that, you'll notice your spreads get a little wonky, but you can still do all the probability calculations you would have done on the normal distribution. It's just got a strange spread, yo. I shouldn't use yo. I'm too old for this. Bye.